Hello, we are Team Ocean6. We are working on enhancing OpenAI's GPT OSS with multimodal vision capabilities extensible to ISRO Earth observation data. The key challenge that we're trying to address is how do you efficiently and robustly align visual data with powerful language model. Instead of using complex attention mechanisms, our solution is built around the Align module, which is a novel and lightweight connector. Here is where our innovation lies. We are forcing the model to describe what it sees using the language and concepts it already understands. This ensures the visual features are mapped to a region that LLM can effectively interpret, leveraging its powerful linguistic priors. The key benefits of this approach are it's highly efficient, it's lightweight, it's naturally robust to noise, the training is modular and effective. Now, before we jump into a technical approach, let's have a quick demo of our product. Our product is a Vision Earth Observation, which is ISRO Earth Observation powered by GPT OSS Multimodal AI. We are going to ask our model two primary questions. First of all, we are going to ask it some questions regarding development in a region. Now, while the model processes the image, let's have a look at the image. We are trying to ask what's the change in the image from 2020 to 2025. Let's see what our image answered. And as you can see, it clearly detected that yes, there have been some change and the change is corresponding to that industrial zone only, which is correct. Let's have a look at our second question. Here we are trying to query about the salinity levels in the sea and what's the particular cause regarding that. And as you can see, our model is saying that yes, the text report explicitly highlights some abnormality, and based on the visual evidence, the likely cause is the coastal vegetation. So as you can see, our model is doing pretty well. Now let's get back to the technical jargon. The approach first extracts key spatial features from the visual input. These features are then passed through a two-step align module. The module's first layer converts the visual features to the language model's internal size, and the second layer projects them into the vocabulary space, producing a probability distribution over all the possible words. The distribution is used to create a semantically rich visual prefix by combining the language model's own word embeddings. Finally, the visual prefix is attached to the user's language question and fed into the large language model to generate a precise and visually grounded answer. Coming back to the methodology and working prototype, the key programming language that we are using is going to be Python, and we are using PyTorch and Hugging Face transformers for deep learning frameworks. The libraries that we are using is going to be transformers because we are interacting with visual encoders, and we are going to use NumPy, Pandas and HDF5 formats for handling large datasets. We are planning to use 880GB GPUs to accelerate our program. Apart from that, we are also planning to use Docker for reproducibility and WAN-B or TensorBoard for experiment tracking. Now let's get to the feasibility and viability of our approach. The heart of our solution is the GPT OSS 120 billion parameter model. Honestly, this thing is a beast. It's already performing nearly as well as the huge SOTA models in reasoning. And from the practical side, we have made sure that this isn't some theoretical project. We specifically designed it to be efficient so it runs smoothly on a single A100 GPU. Okay, so where's the catch? The biggest technical hurdle is getting the model's vision side to talk to the language side. The real trick? Merge these two words, the visual and the text, without breaking the powerful language skills the model already has. How do we fix it? The align module is the fix. It's lightweight, projection-based alignment layer we need. The best way to think about this is a small and smart adapter. It doesn't just map vision to language, it translates visual data into the LLM's own native semantic space by using its text embeddings as the building blocks. The direct alignment is both elegant and incredibly effective. Coming to the impact and benefits of our approach, the impact of the model goes far beyond standard LLM or VLM. With an open source model possessing capabilities similar to top tier proprietary models, we are looking at better decision making across various domains. The impacts are split across three major areas: strategic and national impact. This allows for secure in-house processing of sensitive national data. The model's enhanced robustness makes it reliable for critical applications in urban planning and infrastructure monitoring. Coming to scientific and industrial impact, the tool can provide assistance in medical imagery analysis where its robustness to noise is a key advantage while ensuring full privacy preservation. Coming back to the economic impact, the efficiency and lightweight nature of the Align module makes this powerful model more accessible. This can help foster the startup ecosystem by providing an easy to use, reliable model that can form the basis for the new AI as a service applications. And we have used these references. For our core architectures, we heavily drew in for inspiration from the Align VLM 2025 paper. Thank you.